my pleasure today to welcome our guest speaker for the Department Colloquium. And this is someone that I actually know quite well, that Liang and I met first in 2011 in College Station at Texas A&M University. And we've had the opportunity to stay in touch since that time. So Dr. Liang Chen did his bachelor's and master's at Lanzhou University, and then did his PhD from the Department of Geography at Texas A&M in 2015. Following completion of his PhD, he went to COLA at George Mason University, where he worked as a postdoc with Paul Germeyer for 3 years, and then in January of this year, he moved a little bit closer to us here in the Midwest and joined the Illinois State Water Survey as a research scientist. And he is currently there on the campus. So the Illinois State Water Survey is on the campus of the University of Illinois at Champaign-Urbana. Liang's research you'll see and hear more about today, but he is interested in land-atmosphere interactions, hydroclimatology, hydrometeorology, climate modeling, and he uses a variety of different approaches, observations, and models to investigate questions in and around those topics. His research has been published in a variety of the top journals in our field in climate, Journal of Climate, JGR, and he has one that's going through the ringer at Nature Communications right now. So Liang also received the John Russell Mather Paper of the Year from the Climate Specialty Group of the American Association of Geographers in 2016. This Paper of the Year award is the recognition that geographer-climatologists give to the best paper that was published by a geographer in the preceding year. So other than that, all I can say is that I can also tell you sort of other stories about Liang since I was on his dissertation committee, but I'll save those for more informal introductions later, but if you want to hear about those. And it's a great pleasure to have you here in the department, and please join me in welcoming.
Thanks, Stephen, for your kind introduction, and thank you for coming. So, as Stephen mentioned, my background is a physical geographer, and since I started my postdoc, I was more focused on the climate modeling or the land surface model. So today my presentation is about land urbanization and climate. So actually. So about the urbanization or climate change in China as part of my PhD dissertation, and since my postdoc work, I'm mostly focused on the global model, global climate model, using the CSM. So I'm looking at the land-atmosphere interactions at the global scale using the CSM2, using the CSM or the satellite data. So today my presentation, so half of it is about the urban and climate in China, and also some work I did about the land atmosphere interactions using the global models, but we will focus on over China. And so I will provide some strategies about how to deal with global climate warming. So just to give a very quick background about the global climate change. So the figure on the left is from the IPCC or 5 report. That's from the SMAP5 model ensemble simulations about the future climate change from the RCP 4.5, which is medium emission scenarios. And the left panel just shows the temperature change in winter and summer, so we can see the global temperature increase. And most of you should be familiar with the pattern that the greater increase in temperature in winter and in a higher latitude. And interestingly, the figure on the right that shows the equilibrium temperature, climate sensitivity based on the SMAP6 simulations. So historically, or typically, so equilibrium climate sensitivity, that's about how the surface temperature responds to the double CO2 concentration relative to the pre-industrial situation. So historically, the recommended level is between 1.5 to 4.5. But here, if you look at the numbers of the equilibrium climate sensitivity, and you see that quite a few models shows very high climate sensitivities, like the CSM, a lot of you guys here using. And so that's the result. I think I got this figure from the Twitter, but this was cited by the editorial of Natural Climate Change last month about talking about the landscape of the SMEP 6 models. So you can see that the higher climate sensitivities from the newer version of the Earth system models. And there is another paper published this year from the CSM2, which is the new version of the CSM from NCAR. And it's also confirmed that there is much higher, there is a higher climate sensitivity compared with the previous version. So this just want to show that so this high climate sensitivity translates into the more temperature increase in the future, or the period with fast temperature increase. So that's the background about the global temperature increase. So we know that the temperature will increase, but what we can do at land. So this is a statement published this year from the American Meteorological Society, which is about the climate change statement. And they mentioned that the change in land surface use from agricultural, irrigation, deforestation, and urbanization can influence the surface exchange of the water and energy with the atmosphere, so they can influence the climate at the local or regional scale. So it just gives an idea about the land-atmosphere interactions. So in my presentation, I mainly focus on the biogeophysical feedbacks. So there is no carbon, there is no nitrogen interactions between the land atmosphere in my presentation, but of course it's also very important for the global climate system. But here we only focus on the water cycle or the energy cycles. So they're from the atmosphere to the land. So there's precipitation, there's the radiation, but also there's the feedback from the land surface through the evapotranspiration or the reflection of the radiations. So the whole idea of this presentation is about how the land atmosphere interactions through the land surface or land use change. So we're talking about the biogeophysical feedback. So that controls the energy, water, and the momentum exchange between the land surface and atmosphere. So if you look at the figure on the left, so that we can consider the land use of land cover change. So for the tree or grass, they have different albedos, so they can reflect the solar radiation with a different ability. So for example, for the tree, they have a lower albedo compared with the grass, so they have a warming effect. But also when we consider the evapotranspiration of the land surface from the tree or grass, so typically the tree can have more evapotranspiration than the grass, so there has a cooling effect. And talking about urban, so the urban has a different albedo and also have a different surface roughness, also the different vegetation condition. So all this change can influence the climate at the local or regional scale. So because this talk is about the urban in China, so I want to show that how the urban expand in the past few years, or how it will change, how it will change in the future. So that's a paper published recently. That's not me, but people have the same name. So that's urban expansion from 2000 to 2010, and you can see the black color, that's urban in 2000, and the red color, so you can see how much increase in the past in that 10 years. And also there is the urban projections, so from 2000 to 2030, and mostly over the eastern part of China. So there is an encroachment of the urban area into the farmland, so replace of the cropland with the urban. So my presentation will just include 4 parts. So how the climate change in China, and how we consider the urban in the climate model, and to see the impact of the urbanization on the future climate. And also we can offer some potential strategies of the climate change mitigation, and I also talk about some my current work and the future plans. So hopefully we can get some similar research interest and work together in the future. So this is from the SMEP 5. 20 GCMs, and I think most of you are familiar with kind of figures. So the temperature increase in different scenarios. So RCP 8.5 has the highest temperature increase, and RCP 4.5, even it's a medium emission scenario, also have a temperature increase in the next few decades. And RCP 2.6 is a much stable, and you can see the temperature increase to by 2040, and then the temperature get more stable. And here it just is a temperature trend in RCP 4.5 or RCP 8.5, and or the temperature difference compared at the end of the 21st century compared with 1971 to 2000. So you can see there's a much warming over the RCP 8.5 all over the country. And here just to show the temperature extremes. So we call the TXX, that's the temperature of the warmest day of the year. So basically that's the maximum value of the daily maximum temperature of the year. So again, so RCP 8.05 shows a larger increase, and it can be reached, increased by 5 degrees Celsius. And RCP 4.5 also shows an increase in the temperature hot extremes. So which means more probably. It just shows the intensity of the hot extremes. And especially also you can see how the temperature change or the TXX change, and there is the largest change over the eastern part of China. That's where related to most of the urban area are located that I showed you before. So there's something uncertain inside the symmetric models or the GCMs. So when I do my PhD, I realized that a lot of the symmetric models, they never considered as a change in the urban area. So even now, we check the map, the landing curve map from the CLM, which is a landing component of the CSM2. So they have like, this shows how the urban area in the pre-industrial condition, which is 1850, and the urban area in 2000. So they never considered the urban change in the historical period. Of course, this is not real, right? So the first experiments we did is about how the land use change impacts the climate that we use, and we use a CSM model. And if we didn't consider the change in the urban, so that's the change. That's a situation where in the historical period that includes the deforestation over most of the region of the country, and also there is a change in grassland, and of course there is an increase in cropland. So that's the first experiment with current land cover condition, which is 2000, and with a historic pre-industrial condition, which is 1850. So this too doesn't consider the change in the urban area. And also we did actual experiments with that we cleared. You see that there is urban area. So we removed all the urban area and redistributed the fraction into the tree or grass or crops proportionally based on their distributions. So we had 3 experiments. So the difference between 1850 and 2000, that can be the impact of the vegetation change. And the difference between 2000 and the 1850 no urban. So that's a combined impact of the vegetation and the urbanization. So that's a more realistic consideration about historical land use on the climate. So here we just show how this change that influences the temperature. And the top panels are just the natural impact, which is just as a difference between 1850 to 2000. And the bottom one is a combined impact from the natural vegetation change and the urban change, and the urbanization. So the left part is the Tmax, the maximum temperature, and the red panel are the daily minimum temperature. So you see that in summer, and so for the vegetation change, actually it shows a cooling effect. So mostly it's because of deforestation and with the increase in cropland and grassland, it actually increased the evapotranspiration. I will talk later, probably this is not real in the observations because something wrong with the model. Probably it's wrong. Anyway, so for the deforestation or the historical land use land cover change, it has a cooling effect in summer and a warming effect during winter. So mostly that's because albedo effect. So remove the trees with grass, so they will increase the albedo. Yeah, that will increase the albedo. But, yeah, so it causes a cooling effect here during the day for the daily maximum temperature. But if you include the urbanization in China, and you see that especially in daily minimum temperature, it has a much warming effect. It has a much warming effect, especially in winter. So the urban effect is very important during night and also important during the winter. So if you just calculate the average temperature in summer and winter, also compare between the natural and the combined effect. So during summer, there is slight warming on the mean temperature in summertime from the urban area. So you can see there's the Beijing area and also that's the Hong Kong area. And in winter, and a strong warming from the urban. So you have to consider the urban change if you do this kind of historical land use land cover change, because it shows a very different temperature impact. So that's the result from the CSM, the global climate model. And also we did some experiment with the world. So we considered how the urban change in the future in China. So this is just the probability of the urbanization in China by 2030. So we can get a map of present urban area and also the future urban area. So we just have this sensitivity experiment inside work and to see how this changes the surface temperature. And of course, the urbanization or land cover change also influence the circulation, but here I'm mostly focused on the temperature, so I'm not showing here, but if you're interested, we can discuss more later. So we have 3 experiments, so historical run, just the down-scale historical simulations from the CSM, and also we have future downscaling from the RCP 4.5 of the CSM simulations, and also we have a downscale RCP 4.5 simulation that also considers the future urbanizations with this map. So the difference between the historical run and the RCP 4.5, so that's basically the impact of the greenhouse gas forcing. And the difference between the RCP 4.5 urban minus RCP 4.5, that's the impact of the future urbanization on the local climate. So here we can just mostly focus on the 3 regions in China, so Beijing, Shanghai, and Hong Kong. And so the figure on the right, so that's a near surface temperature difference between near surface temperature between the urban RCP 4.5 urban and RCP 4.5. So there's a strong warming in summer, and there's also significant warming in winter, but most of the warming happens in summer. And if you're looking at the down cycle, most of the warming happens during the night. And this just to show the turbulence fluxes change due to the urbanization. And there is a decreased latent flux because after the urbanization, so mostly because of vegetation change or the soil property, and also because of decreased evapotranspiration or decreased the latent flux, it will increase the sensitive heat flux. That's why you see the large warming effect over the urban area that's shown here. And if we calculate the temperature impact at the regional scale, so we just calculate the average of the temperature difference over the square area. That's a regional temperature impact based from the greenhouse gas impact or from the urban impact. And the local impact, that's just the focus on the urban area that happen in the future. So 50%, I think it's a 30% area is urban. So we just calculate the temperature of the local impact. So you see that actually, so there is very comparable impact of the greenhouse gas and the urbanization, especially at the local scale. So you see here the urban can increase the temperature by 1.8 degree, or in summer it can be as high as 2.7 degree. But for the greenhouse gas force, like at 4.5 scenarios, the local impact is about 1.3. So as a local areas, urbanization can have even stronger impact than the greenhouse gas force. So that's give you a background about how the temperature change in the future and how the urbanization will impact the temperature. And here we want to show some potential strategies of the climate change for climate change adaptation or mitigation. So again, go back to the idea we mentioned before, the land use of the land-atmosphere interactions. So the change of the land surface through the deforestation, through irrigation or urbanization, they can influence the exchange of the water and energy with atmosphere so that they can change the temperature. So at least here, like 4 possible ways, like land use, land management, renewable energy, and urban growth. So first, let's talk about afforestation or reforestation. So back in 1990s, China has started a program which is called Return the Farmland to the Forest. So there's a large area with afforestation or reforestation. So here, I'm not sure you can see it clearly. So the blue dots are just to show the region with planted forest. So that's what we call the afforestation. And if you use, so this study used MODIS data to compare the forested area with the surrounding area to see how the temperature impact of this land management. So you can see that, so the blue shows the cooling effect and the red shows the warming effect. So throughout the country, if you have the increase of forest cover or the reforestation that can decrease the temperature, and especially in summer that we mentioned before, with under the future climate change, there will be a large increase in the heat wave or heat extremes that happen in summer. So you can see that actually, so afforestation or add trees that can have a cooling effect. However, there's some like a modeling work that using the GCM. So the left one that's from the Halley Center model. So the top figure shows how the tree change in the past few in the historical period. So the blue shows the decrease. So over the globe, you can see the deforestation happen from pre-industrial to present period. And so they use some attribution, detecting an attribution way to detect how this TXX trend, which we talked before, that's the warmest day of the year. So there's a cooling effect. So they attribute this cooling effect over this region to deforestation. So keep in mind here, so this that reforestation have a cooling effect, but here from the model, the deforestation has a cooling effect as well. And also we did some study using the CSM last millennium ensemble project. So they have the simulation of the climate from different from individual forces, including the natural forces, the orbital, the solar and the volcanic. And also they have individual forces from the greenhouse gas, the land use, and aerosols. So you can see that the historical land use actually also has a cooling effect to the TXX or the heat extremes. So there is a confliction between the model and observations we mentioned. And there's another paper also confirmed that not only about the Halley Center model, not only about the CSM from ANMAR. So most of the SMAP5 models. So here, if you just looking at the Tmax change on the top panel and the red bar that's for summer, so you can see that. So most of the SMAP5 models or the lucid models show the cooling effect of the deforestation. And from the observations, and they show the warming effect. So there is a conflict between the model and the observations. So we did some analysis using both the satellite data and the model simulations. So here we're just using the MODIS temperature, the NDVI, albedo, and the evapotranspiration to show that how the sensitivity of the sensitivity of this temperature or NDVI or evapotranspiration to deforestation. And we see that using observation or high resolution satellite data, we found that there is a warming effect from the deforestation, which is confirmed by the previous studies
that's because the high, and also you can see there's a high deforestation will increase the albedo and then decrease the evapotranspiration. However, if you run the model, and the left panel is offline simulations, which means that we have the same atmosphere forces for the two experiments we did, like with the land cover in 1850, with the land cover under the deforestation scenarios. But they have the exact same atmosphere forces. So that's offline simulations. We just run the land surface model. And this is a coupled simulations. We coupled the land model and the atmosphere model. So here you can see how this is consistent with, so from the from the offline simulations, and we also found the warming effect from the deforestation, which agree with the observations. But if we couple with atmosphere, so we also have more results to show in our paper, but I'm not showing here. That's because the change of the cloud and also changes the whole atmosphere column, especially in the middle and the lower, in the middle and higher latitude, and you actually see the cooling effect from the deforestation. So that's the conflict between observation and the model simulations. So we also use some other technique to, it's called the subgrade conversion, because inside the GCM for each grade zone, they have different land unit, the forest and the grass. So we can just calculate the difference between the land between the grass unit and the forest unit. So we cause a local impact here. So again, we confirmed the warming effect from the deforestation, and also we found non-local impact from because of the different atmosphere conditions that we saw before, the cooling effect over the middle and higher latitude. So if we combine them, these two, which is pretty similar that we found in the coupled simulations. So again, so the impact of the deforestation or afforestation to temperature or to the climate is pretty scale sensitive. So we just submitted a proposal to NSF, and we want to look at how this related to the model resolution and how this related to the parameterization of the boundary layer, atmosphere effect boundary layer. But again, we can confirm that if we plant more trees or have the reforestation at a local scale, there will be cooling effect. And another strategy is land management. So I was pretty motivated by this paper, which is talking about the cooling of the U.S. Midwest this summer, temperature extreme that can be associated with cropland or agricultural intensification. So the figure on the left, that just shows 95% in maximum temperature trend, and you can see there is a cooling effect. Also, someone also called the warming hole in the Midwest. So if you compare this figure with the figure on the right, which is the SIF, the solar-induced florence, which is a very good indicator of the vegetation photosynthesis or soil moisture or evapotranspiration. So there is a very good agreement between the decreased temperature heat extremes and or crop activities. So the author attributes this like the cooling over the summer cooling in the Midwest can be attributed to the intensified agricultural activities, especially irrigation. So the same thing in China, and so the map here shows how the temperature shows the percentage of the irrigation, equipped irrigation. So most of in the eastern China. And the figure on the right, so if you just look into the right line, that is the increase. So that's an increase in the irrigation area, and it's published last year, but that's not me. So we did some work using both the model and the remote sensing data to detect how this irrigation activity that can influence the local or regional temperature. So this study actually is based for the as a global scale. So we did detect some like irrigated area. Eastern China, but also India or California, Great Plain, or lower Mississippi River Basin. So this map just to show the percentage of area equipped for irrigation. And just keep in mind, so that just shows the area that equipped with irrigation. It doesn't tell you how much irrigated water has happened during the growing seasons. So we're just using this detecting everything on this map. And so there's a moving window of this on this irrigation map. So if a pixel has irrigation area greater than 20%, so we will start in the detecting everything. So we will divide it into the pixels into two parts. So if the irrigation is less than 10%, we call it no irrigation pixel. And if the irrigation, if the pixel has irrigation between minus and plus of the target irrigation pixel, we call it the irrigation pixel. So we use this range to well present the irrigation condition of the central pixel. And then we get these two types of pixels, and if the range, we count the range of the irrigation pixels. So basically, it's just the number of the irrigated pixel over the total pixels. So if the ratio is between 3.5 and 6.5, and we will fix this window, and we can count the difference between the non-irrigated pixel and the irrigated pixels about the difference in temperature or difference in evapotranspiration or soil moisture. So we use this range just to make sure the results was not skewed, a selection of the pixels. So here you can see a very clear, so the top is the temperature difference between the irrigated pixels and non-irrigated pixels. And the bottom is just the difference in irrigation. So just look at the Eastern China, and you see that there is slight cooling from the irrigation. But if you compare with like Central Valley of California or Great Plain, they have much higher cooling effect from irrigation, which can be over 5 degrees or 4 degrees Celsius. And also like India. So we calculated the relationship between the difference in irrigation and the difference in the surface temperature. So we divided into different regimes. Like on the left, you see that very clear relationship between the irrigation and the surface temperature, which is in the arid or semi-arid area, like in California or Great Plains. So that's what we always talk about. So there are much higher sensitivity of the temperature to the soil moisture. But for the regions like lower Mississippi River Basin or Eastern China here, and you didn't see a very clear relationship between this irrigation and the surface temperature. So that's what we call here, like, so those regions are humid, in humid climate. So the temperature or the evapotranspiration is more energy limited instead of moisture limited. So the temperature is not sensitive to the soil moisture. So that's why that even there is irrigation happening here, but we see only slight temperature decrease. And we also did this irrigation simulations in CSM2, and so for different regions. But also you see that there is a large irrigation happened in Eastern China, but there is still a very limited area as a cooling effect that was confirmed from our satellite-based estimations. But there's a thing just to keep in mind. So when talking about the irrigation, because more evapotranspiration, so it can cool the surface. But another thing is, if you add more water to the soil, there is high evapotranspiration that has the potential to increase the humidity. So we talk about the heat waves, and also people consider the heat stress. So it's a combination between of the temperature and relative humidity. So not only decrease the temperature, but also they can increase the humidity. So they can increase the potential of the heat stress. So here, there is a study published last year. So they actually said that the irrigation increased the level of temperature. So that's a variable that people sometimes to quantify the heat stress. And they found that actually with irrigation, so especially over Eastern China, that most of the urban area is, it can increase the level of temperature, which is an increase in heat stress. So just keep in mind the irrigation cooling probably has some negative impact. And another thing is about renewable energy. But this is not quite related to the land atmosphere interactions, but I started this part of work since I moved to Illinois. But most of the work I have done is actually over the Midwest or over the North America. But I talked with some colleagues in China. We also did some work about how the energy will change, renewable energy will change based on the background of the global climate change. So you can see that, so the growth of the wind power and the solar power in China in the past few decades. And there is a paper talking about how the change of the wind power based on the CMAP-5 simulations. And they found that there is a southward shift of the global wind energy. So in the mid-latitude, there is a large-scale decrease in wind power, and but there is a strong increase in the tropics. So that's what we saw here. But again, so this is CMAP-5 simulations. So that's like very coarse assessment, very coarse resolution. So if we want to apply this to the regional scale or to investigate how the wind energy or the solar energy in China, so we probably need to use downscale simulations. So here we just use the simulations from the East Asia Cortex. So that's simulation from different, I think, from 10 combinations of the regional climate model that downscaled the CMAP-5 simulation. So this is just the climatology of the wind speed in China in winter, spring, summer, fall, and the annual mean. So you can see there is a large there is very high wind speed in northern China, or northwestern China. That's where most of the wind power plant was. And if we use Eastern Asia Cortex simulations, and we can get the projected change in wind power. So first, we will extrapolate the surface wind to the wind turbine height, which is 80 meter or 100 meter, and we can and then we calculate the wind power and calculate the difference between the historical period and the RCP 4.5 period. And you can see that actually, which is pretty similar with what we see from the CMAP-5 simulations, the GCM simulations. There's a large-scale decrease in wind power, and but the increase in the southern part of Asia. And another part is how the change in the solar energy. So this is a paper published a few years ago that also uses CMAP-5 simulations. So there's change in the incoming solar radiation and clear sky, solar radiation, temperature, and cloud cover. All of them are very related to the PV power, which is the solar panel power. So based on this, they projected how the change of the solar power in the future based on RCP 8.5, I believe. So there is a large increase in the solar power in eastern China, which probably is a good thing, and also there is an increase in eastern U.S. or Europe. So there's a lot of paper talk about the investment of the solar panel, and it's that there's no, I think there's a paper even published on Nature Climate Change, which talking about it's a no great investment about the solar panel in Europe because of this projections. But what if we're looking at the solar panel, the change of the solar energy from the downscaled models? So the top is that's a climatologist, how the change, how the condition in present situation, and that's the bottom one. It's a projected change in incoming solar radiation. Because if you're looking at the map here, so the incoming solar radiation is very related to the projected trend in the PV power. So here we're just looking at the change in the incoming shortwave radiations. Then actually we didn't see the significant increase in solar energy that is conflicted with what we see here from the CMAP-5 simulations. So what's the reason? And also just want to show this map, this figure. So again, we did this similar thing over US from the GCM and from the CMAP-5 models, and also from the downscaled models. So the black one That's averaged from 38 CMAP5 models. And you can see in the future period, there is a gradual increase in solar energy. But from the red line, that's average from 14 North American cortex combinations. So there is a conflict between the GCM and the RCM simulations. It's not like the wind energy we showed before. So major reason probably is because aerosol optical depth. So the figure on the left that's AOD. So basically from all the scenarios at RCP 0.5, 4.5, or 2.6, it all shows a decrease. It all shows the increase in the optical depth. So because the decrease in aerosol concentration in the different scenarios, which shows agreement with incoming solar radiation, RSDS. So that's what we saw here from the RCP at 0.5. But if we divide the models that have the without transient aerosol and with the transient aerosols, so left that's a model with transient aerosol concentrations. So that you see that because of decrease in aerosol and there will be increase in incoming solar radiation. But for the model with a fixed aerosol concentrations, there is a better change in the subclimate or even decrease, which is mostly because of greenhouse gas impact. So for the Eastern Asia cortex project, so for the downscaling models, so for all the models, they just have the CMAP5 models as the literate and boundary conditions, but they never consider how the concentration of the aerosol in the model. So that's a reason that you see that in the original models, there's no decrease in the annual mean incoming solar radiation, but from the global models, and you see a strong increase in solar radiation. So that's this part about renewable energy. So there's possible decrease when and a possible increase in solar radiation, which depends on the how you consider the aerosol concentration in the model. And the last part, that's what we did since I moved to Illinois Water Survey. And but we are developing some ideas and proposals about how this urban roof, including the green roof and this cool roof, how that can be used to mitigate the warming at the local scale. So this from my colleagues. So we developed the parameterization of the green roof and the groove. Basically, the groove is just the wet roof, so increase the surface albedo, so that decreases the surface temperature. So that applied this model into the Chicago area, and you can see the strong local cooling because of the green roof or the wet roof. So we also want to use this as a strategy that applied to the model that can be used for the region in China. So go back to what we did before to consider the urbanization in China. So also we probably consider the green roof or cool roof in the urban area in China. And another thing is we want to look at how this impact of the urbanization or the roof, different roof across the scale. So this is a model that that's a CSM model, but we have a different grid configuration on the left. That's what we commonly use. So for each grid, they have the fixed resolution. But here, we also want to use a model with a variable resolution. So we can have a focus of a certain area. For this one, we just focus on the over the United States, but we also want to apply this to China or some region that we're interested. So we can increase the resolution at a certain area to see how this impact will change if we have the different resolution or at the different scales. So I want to conclude my presentation here. So just want to show that there is significant warming and intensification of the hot extremes in China based on the CMAP5 simulations. And we also found that for the urban effect and historical urban change or future urban projections, they all have significant impact on the local or regional climate. And also we provide some local or regional practice to land atmosphere injections to decrease the temperature using different ways, like the afforestation or irrigation or the roofs. So I think I will stop here and I will be happy to answer your questions.
For the land vegetation change, it shows some show cooling, some show warming. I'm just wondering, when you have more vegetation, so from moisture perspective, I'm wondering what is the mechanism for the cool and the warming?
Oh,
Yeah, maybe we should.
so for this, I mean, we call for this analysis or for the offline
Just in general,
simulations.
physically,
Yeah, physically.
potentially, what is the mechanism? If I, reforest, then forest again, what is potentially the mechanism? Cooling or potentially warming? Just physically.
Yeah, physically, so for the local effect, that there is a increase the forest cover. So first, they will decrease the surface albedo. So it has a warming effect. But on the other hand, if you have a more tree cover, it can enhance the evapotranspiration. So it has a cooling effect. So it has like a competition between the warming and the cooling, depends on the vegetation features. But so mostly so there is a conclusion, agreement about the impact of the forest change or deforestation. So in the tropical area, so probably the evaporative cooling has a much stronger impact than the deforestation in the boreal forest, which has a stronger warming effect because of the albedo effect. But the issue is more in the middle latitude. So it can be cooling, it can be warming. So for here, so our point here, we just want to show that, so as a local scale, if we didn't consider the feedback back to the atmosphere, so basically it's warming because of less evapotranspiration after deforestation. But if you consider the feedback, so we're not sure, so that's why we submit algorithms to see how this feedback to the atmosphere can change because of resolution or because of parameterization in the model. So if we consider the feedback to the atmosphere, we will decrease the whole atmosphere column. And also we can possibly increase the cloud cover in some regions. So that's probably why in the middle or higher latitude it has a cooling effect.
Yeah, so my thinking, this is one model that you showed.
Yeah, this is one model.
So would that be possible for another model where data is more important? So even with offline, you can cool.
It's possible. Yeah, but we work with, let me see. So first, habit center model, for sure, they have the same issue as us. I'm not sure it's a cut issue or it's a thing we cannot validate. And also the model, what's it called? The X-Plant Institute in Germany. They also have a paper published recently about the warming as a local, but cooling as a non-local. So not only about CSM, but also from other modeling centers.
Yeah, have you looked at something like the monsoon change deglobalization?
Yeah, we have, so for this paper, yeah, we're looking at how they change in the over monsoon season, during the monsoon season. I think, I cannot remember, it's a strengthen of monsoon because the temperature gradients in the ocean and the land. Yeah. Yeah, but for sure, we definitely look at how they change in the precipitation and the large scale simulations. And that's not shown here.
Would reforestation also cool in the sense that it's a carbon sequestration? because the photosynthesis would be a natural way of carbon sequestration.
Yes, I think so, but we're not looking at the biogeochemistry part. We didn't consider the carbon part in the model.
But that might be a bonus or something.
Yeah, definitely that's a bonus, yeah. So it would theoretically absorb more carbon dioxide from the atmosphere and fix it.
Yeah.
Yeah, so that's definitely a strategy, but mostly I'm just looking at how the physical or biophysical feedback to the atmosphere through the turbulence fluxes or the albedo.
But in addition to that, if you, over a long term, eventually if you lower the CO2, then you would counteract the greenhouse concern.
Yes, yes, definitely. Yes.
Are you concerned with downscaling the global RCMP models to like nation scale like China? Are you concerned about errors kind of propagating to a smaller scale?
You mean even higher scale, what I showed here, or?
I mean, you were just talking about downscaling, taking a larger global model and then kind of zooming into China.
Yeah.
Are you concerned about like it being less accurate when you take a model that was designed to look at sort of a global scale type thing and look at something much smaller than the globe?
Yeah, so that's why I mentioned here, one, looking at the impact across the scale. Sorry. Yes. So we want to do the exactly same experiment about the urbanization or the land use change, but in other experiments it will be exactly the same, but we will just change the resolution of the model. So from like regular GCM resolution like 1 degree down to 4 kilometers or even higher to see how this feedback will be different.
Okay.
Yeah, but it definitely will be a concern in the future.
I wonder when you measure the urbanization to the climate change, I mean, how do you like uncouple other factors like the global warming trend?
Uncouple.
Yeah, I mean, like there will be other factors that contribute to the when you measure like the surface temperature, there will be a trend and the surface temperature increase. But there, I mean, except for the urbanization, there will be other factors contribute.
Yeah, definitely. So that's why we just did a sensitivity experiment, and we compare that. As you said, there's different factors to influence the temperature. So yeah, so here, so the left part, that's basically how the impact of the global climate change, like a greenhouse gas increase. So how that change the regional or local temperature. And the right column is just the change in the impact from the urbanization. So this is just more like a sensitivity study. So increase the urban area, but we have everything else the same. So we just want to isolate the impact of the urban area.
I would like to follow up on that question. So in your presentation, you mentioned that the urbanization will kind of lead to warming and the irrigation have the cooling effect. And I noticed that both the urbanization and the irrigation area is located like in the eastern part of China. So do you think or do you consider the changes in temperature in the eastern China is the combined effect of the irrigation land and the urbanization land? And do you think the urbanization land have a counteract effect with the irrigation land when they play a role in temperature?
Yeah, there will be like combined effect, but I mean urban area or the cropland are at different place, right?
Okay.
So as a local scale, if you just look at the urban area, probably, I mean, of course the urban heat island effect have play a more important role, but over the irrigated area, so irrigation play a more important role. But we didn't consider more like a remote impact or something. but it definitely should be considered that, okay, so if you add irrigation in this area, so how's the temperature or how's the precipitation change at the downwind area? So that will be definitely a concern. Yeah. So there definitely will be a combined effect. And also what we talk here about the green roof here. So basically they just add the vegetation on the top of the roof. So they also actually have the irrigation happening for that green roof. So that's a bigger reason that the green roof can reduce the surface temperature of the urban area. So that's like an urban irrigation. Yeah.
So you presented 4 climate change mitigation strategies. I'm just wondering why you selected those 4. Like, is it because they're well studied in the literature and have like known biophysical causal mechanisms, or just why did you select those 4?
What did I select the 4?
Yeah.
I think so. Land use, basically the afforestation, because in China, as I mentioned, so the program of the return farmland to forest that starts since the 1990s. So that's definitely a pathway to do the investigation on how this program impacted the climate or temperature. And the land management, so that's mostly motivated by the paper I mentioned, and also they have a paper talking about it's called effective radiative mitigation, land management mitigation way, including irrigation, but also there will be like, I didn't mention, it's called no-till farming, if you know that. So basically there's no tillage throughout the year for several years. So that not only, so from the biogeochemistry perspective, so it can keep more carbon to the soil, but from biophysical perspective, it can increase the albedo of the surface. It has a cooling effect. But I didn't show too much about, I didn't do any work about how the no-till farming will change the local temperature, but for sure that's also a possible strategy for the temperature or warming mitigation. And the renewable energy, that's mostly just because my current work at Illinois. So we're talking about the renewable energy in Illinois. I'm not sure if I told you during the lunch that they proposed that Illinois wants like 100% renewable energy by 2050. We're not sure it's possible, but it's just a direction about how the renewable energy will influence the power plant. So it will be the clean energy, so less greenhouse gas greenhouse gas will emit to the atmosphere. And another part I didn't show here, but I included here. So if there is a large-scale installation of like solar panel or the wind farms, definitely have the impact on the lower atmosphere or even the ecosystem. So we're trying to develop a proposal to talk about how this renewable energy development influence the natural system. And yeah, pretty much. So urban roof. So we're talking about urbanization. For sure, we want to mitigate the global warming, but we also want to do something over the urban areas. What we can do over the urban area. So the roof, the change on the roof is definitely a strategy. So.
I was curious in the studies how I know, so I'm very curious how in the models you understand and gauge and project urban expansion. So presumably the projection of temperature changes and the effects projected into the future that you in your studies suggest that there's a certain amount of change in the urban area that you had some now shown. So what feeds into the calculation of the change in urban area, since that's very much in dispute in terms of what are the drivers and mechanisms, this relationship between economic growth and demographic change and migration is pushing built-up urban area?
Yeah, but first, that's not my study area, so I got so basically the result from a professor when I back in Texas A&M. So yeah, they definitely consider the economic growth or the population growth in China. I mean, this is like a global data set about the urban projections, and yeah, so that just grabs the data and and prescribe it in my model to see how they change. But for sure, so that's you need to consider.